konuşmamızı Habib Hoca yapacak. Dear Professor Dr. Habib Mazharimousavi, as a presenter, you are kindly requested to deliver your speech on understanding of universe from Maxwell to Einstein. Dear Professor, please give your speech.
Yes, you hear me? Good afternoon, everybody. So I'm sorry, John. My speech is prepared for students. If it will be boring in advance, I apologize.
It's a pleasure.
Thank you very much. And also, I would like to say I'm very happy to be here teaching high school students. I hope we will learn something, and we will learn something from what I will say. And also, I hope you enjoyed the 2 days workshop. And I'm sorry that I speak in English, because you, I think, expected everybody talks in Turkish. But you should get used to it, because English is the language of science. So no matter what you think or what I think, at the end you have to get used. Anyway, I will try to go slowly.
You take it, hocam, so I can take this.
Yeah.
It's the connection problem. That's
So this is the very good. This is the technical. This is the Okay. No. Oh, it's okay. Do you hear me? Nobody hears me. Can I make it worse? Yeah. Okay. So, wait and wait and shake. And below that is the last. Okay. This thing doesn't work. Okay. Okay, I will just take it with my. Oh, yes, yes. Now, I think you hear me. Do you hear me, guys? Okay. So, I was just starting. The subject, as you see here, is just understanding the universe. And also, I mentioned from Maxwell to Einstein. Actually, this is the period of history which physics changed. The revolution happened. So you were on the skies, the space, since yesterday morning, and even before I started the other lecture. But I'm going to take you down, and we walk a little bit on the ground and see what we have other than what we expect to see in the space. So we don't have access to space, I think you know that. Whatever we see, only we observe. Nobody went there to see if there are those things that we are interested to see. But the thing I'm going to tell you, you can see here on our Earth. So I'm sorry that I have to hold it like very close. I think microphone also became tired. Actually, there should be. Anyway, it's okay. Not okay? Oh, these two? Okay. So, I think I should sit. And then you will hear me better. Now, I think it's okay. So I will try to fix my position. Then, if I don't break anything, we will finish this session again. Okay, guys. So now, as I said, during the late 19th century and the beginning of very early 20th, a revolution occurred in physics. So what we see or what we hear these days, even the thing you heard from yesterday to even now, using the technology we are having trouble with, and the other thing all came from that period of time. So I'm going to show you what happened exactly, and I explain those fundamental concepts as much as you understand, and then we will just go as much as we can, but the time is also limited.
Hocam ekleyin. Could you interrupt me? I can stay ready to go for yeah. A lot better.
Okay. So before I can handle this, I think my time will be over.
Don't worry, we will give you more time.
That is what I need for now. Is it okay? Will it be okay?
Okay.
So now let's open all microphones maybe. But then it will be fine. I think I don't need this. Okay, I see, I mean, the first page, the title page, sorry guys. So what is the content of this talk? As I said, I'm going to give you a kind of historical, let's say, transition from 19th late to early 20th century, and give you those phenomena that were discovered and actually changed our life, our world entirely. And within this talk, I will mention many physicists. I try to arrange them in terms of their birthday, actually birth year, let's say. But the achievement might be a little bit, changed in order in the history. But anyway, I try to keep my best, as I said. So although I said I'm going to start from Maxwell, but the best non-physicist in the world is Newton. I cannot just leave it aside and start from Maxwell. So Newton is a symbol, a kind of icon for every physicist. When you come to university, no matter which branch you are studying or what you do, even the medical sciences, they also take a course. And in the first course, they take what are the Newton's law. So it seems that Newton's is part of everybody's, scientific and also ordinary people's life. And that's why I put Newton in the first place. And I think you are familiar with Newton's law. The laws of motion, first, second, third. But what is concerning us here, the fundamental law of gravity before Einstein. Einstein was in 20th century. So now Newton gave the fundamental law of gravity in 17th century. So
He died in 1727.
27, you mean? Yeah, it was 26 or 27. I decided to kill Newton earlier and yes, it wasn't sure when he died. So anyway, thank you, John. Anyway, what Newton said, Newton observed actually what we see every day. So things that are falling toward our Earth. So he, at the end, gave a theory. So the theory of gravity, Newton's theory of gravity. And according to the theory, the masses, two masses, if you hold two masses, they attract forces, actually, a kind of interaction between them happens, and attraction force takes place between them, and they just, how we realize, usually ordinary people in those days, also ordinary scientists, they also knew such thing could happen, or it happens, but they couldn't, make a formula for that, and that is the formula Einstein gave. Newton gave. So in this theory, other than G, which is constant depending which system you measure the force, masses M1 and M2 are the masses of two objects or particles, and B is the distance. And this was actually in 1987 in his book, Principle, he just explained. But of course, as I said, this was a theory. So it took almost 111 years after then somebody made the experiment exactly to prove that Newton was right. So the theory came before the observation. Okay, then after Newton, I think since everybody from even high school student, they are familiar with that, I just move one step ahead. Actually, this one step, it takes almost 100 years. So we come to Coulomb. Coulomb, or Coulomb's law, everybody again nowadays they know. In addition to mass, they said particles, they may have another property, they call it charge. So this electric charge, which we call it now, unlike mass, which always is positive, it could be negative or positive, even zero. So, and Coulomb said the mass, the particles which they have charge, they may attract each other, they may repel each other, or they may do nothing with respect to each other, depends on their charge. And that is how you see here the Coulomb's law. Actually, let me just explain. This force is a vector force, and for the Newton's law also. But I didn't want to make it more complicated. So, you know, this is the magnitude of the force, and if the charges are the same sign, it is, you know, positive. If they are opposite, they attract each other. If one is zero or both, there is no force. But the form of the law is very much like Newton's law. You see, it's exactly the same, but only the constant change. The mass is replaced by charge, and then distance the same. And the inverse square law again takes place here. So this was exactly in 1785. So from now you just calculate, and this one actually Coulomb did the experiment himself, unlike Newton, which gave the theory, and after 100 years they discovered experimentally. He did the experiment himself. This is the device he used. So why it was difficult? Because the force between two charges, even two masses, is very small, and the calibration or the observation with those technology at that time almost was impossible. So anyway, Coulomb gave his theory, and the Coulomb law, of course, is very well known. Also, it is given in freshman student in most of the branches, and we go just before I go one step ahead. We remember in nature there are forces. I mean, I'm going to ask you how many fundamental forces we have in nature. Anybody knows from the students? I mean, from students in high school. Do you know how many fundamental forces we have? 4 forces, yes. And 2 of them already I mentioned. Of course, electric. This is just electric force, but we can later on we call it electromagnetic interaction. Anyway, we go on after. You just look at also the time, the you know, the period these people they live. This is also very important, because I was very careful to make sure these data are correct and, as I said, in order. So almost in let's say first half of the 18th century, Coulomb gave the theory, and then in the second half we have development, and this development, one of them was done by, of course, not only Ampere, but since we know as Ampere's law. So this Ampere's law we teach in to our students first year, Physics 1 or 2. So it tells you that, as you can see here, we have a quantity here which is related to. Anybody knows what is phi e? Okay, maybe it would be better I introduce phi e here. It's electric flux, actually. Okay, and anyway, it tells us magnetic field. B represents magnetic field, is produced by actually electric current, and also if we have electric field, which is time field. Understood? So in previous equation which Coulomb proposed, we have electric charge, we call it Q, and then they attract or repair each other. But the thing is, there was nothing about magnetic field. Actually, magnetic, let's say, theory and electric theory, they were going, just separately, to their destination, and nobody knew they have relation. So, but experimentally, sometimes they realized they are not as separated as they were thinking. So, this is one of them. And we will come back to this term again later. And there are some constants here. You may be interested what they are. So, actually, mu zero and epsilon zero, electric permittivity and magnetic permeability, they are called. But they tell you the structure of space. I mean, here is just vacuum. So if you go inside any other material than vacuum, then they change. So that is the signature of the space, our electric or magnetic field there. So this is the first law, actually the one of them, which connects magnetic field with electric charge. So as I said, similar to Coulomb's law, we don't have for magnetic charge. I mean, for magnetic field, let's say. So what is field? What is force? These are concepts very much related, very much linked to each other, but we don't have time to go much inside. So just keep it as it is. What we see here, as we will see also in Maxwell equation, this was discovered by Ampere and also Ørsted. So these names should be familiar to you. Maybe if you are you come to university, you will see them more frequently because they are the units which we of quantities which we use. So for magnetic field, for electric field, for magnetic strength, for other stuffs. So the name of these scientists are chosen to be used over there. Anyway, so look at the time just again. Ampere and Ørsted, they did almost the same thing, but when you look at the birth year of Ampere, he of course was first. Okay, now we come to Faraday's law. These are the things you hear. Faraday's law is used to generate electricity, even nowadays. So in all electric generators, we use it. So, but it was discovered almost 1831. So from now, more than 200 years ago. So now, at that time, still they didn't know. This E represents the electric field or electric potential, and this IB is just the magnetic flux. It tells you that, I mean, shortly speaking, if magnetic field is changing in time, we will have electric. So, but of course, it is deeper. And as you see, this is the elementary apparatus that Faraday used to show how changing the magnetic flux produces electricity. So I give these names and these experiments. You can go further by looking at the literature. And also we have other guy, Henry. Also at the same time, Henry also discovered the induction law as Faraday, but almost 1 year after. So Faraday did in 1831 in Europe, and this guy did 1832 in USA, in America that time. But now we know it as Faraday's law because he was failure. But only one, and they did independently. I mean, this guy Henry didn't know actually. But Henry also is famous for his other contribution in electrodynamics, electromagnetic. So, for example, as if I'm not wrong, he invented solenoid, and his name is also for impedance, inductance, sorry. And this L here, this is the physical or electromagnetic quantity, which shows that if you have, suppose that you have a seed, and then you put a battery and a switch. So these days, you just switch on, and you see the light is going, coming. or the circuit is on. I mean, everything is okay. But the thing is, when you open the switch, then the electric current is going from 0 to some, maximum value, whatever it is. This current, which is time dependent, produces a magnetic field, which is opposing, increasing the current. I mean, the opposite direction of the initial current. So what happens? So it is a kind of self-resistance against the current. So then the battery should work to overcome this resistance. That work, extra work, because you will not see it after it comes to a steady state. Then that energy spent by battery, it will be stored in the system, and that is exactly used. And how much it is? It is half Li square. I here is the final current, and L is, as I said, inductance of self-inductance of the system. So this was discovered by this guy, Henry, and it is one of the constant device in most of the electronic device nowadays. Okay, so after Henry, 1797, and he lived long. Usually scientists live long, but unfortunately, the one who should live long, he didn't, and they didn't actually. We come to my starting point. Actually, we are at the beginning of 1831, where this guy. You know what is actually? You see his name, Maxwell. Yes, this guy is one of the let's say promising guy who should live longer than everybody, but he lived very short. And you can see here the Maxwell equations. What Maxwell did? Maxwell was very genius. Let me just go through his life, because you as a student, I suggest you go and either watch or read about Maxwell, because it gives you inspiration. I mean, what to do. He was only 14 years old when he gave his first paper. This is his first paper. And he was, of course, at the end, he became mathematical physicist. Okay? So, what was his first paper about? He was very much, and they were also very rich. His father was a lawyer, and they were Scottish. And did I mention? Yeah. So he didn't need to work, but he just left a comfortable life to spend his, devote himself to science. Understood? Because he was enjoying most with science. As I said, in 14 years old, I got promised to give me longer time than usual. So I hope there is no limit for knowledge.
The bus will come at 5:30.
5:30?
Yes.
No, don't tell me now it's 5.
No, yeah.
It's 5:20.
It's
It's still more.
okay.
More
So
than
then,
1 hour.
okay, very good. So because I need time
Session time.
to go through the details. You know what it is? Everybody is familiar with ellipse and other things, geometrical, graphs. And ellipse is one of the, very interesting one. When you try to draw an ellipse, because the definition of ellipse is the points on the paper, let's say, which the distance from 2 points, foci, we call them, are the same, constant. Okay, circle is the points in a paper, a flat paper, with the distance from one single point are the same. This is the definition of circle, understood? But the ellipse is just the distance from 2 points. So now the question is, this guy said, okay, why we should take the sum of the two distance to be constant? So let's take sum of 1 plus an integer multiplied by the second to be constant. Okay, so this is from theory, it's okay, and we can propose it. So you just take, an oval. So you just draw an oval, and then just take a piece of string, fix the end of the string, and take the middle point, or you put your pencil there, and then if your pencil is free to move and you just draw, you will draw an oval. So now he said, in this way, the distance from every single point on that oval and the foci will be the same. I mean, the summation of the distance will be constant. So he said, if we make one distance and the other 2 times of the distance of the point with the second foci, or 3 times, what will happen? So it was just an idea, but okay, as I said, you can give such proposal. He was just 14 years old. I mean, younger than you, most of you. So the point is how you draw it. So when you're going to draw an oval, you can do it easily. Just take a string, piece of string and do it. But when it comes like that, he explained in this paper how to do that, understood? And he generalized it. And then while he was presenting his paper in front of Royal Science Society at that time, he was so young that he couldn't, I mean, they didn't allow him, or he couldn't. A professor, mathematical professor, he was just, he was sitting there, and the professor was representing what Maxwell did. So you can see how clever he was in that age. And then he didn't stop. He just improved himself. And then he solved a long-standing problem at that time. They knew, Galileo even, they observed the Saturn, ring, but they didn't know what is it. They could only see. I mean, it's beautiful ring, as you can see here, but they didn't know what is it. So it's just, you just imagine, even now, I don't know whether you are aware what is it, but it's so beautiful from distance. But nobody knew what is it. There were many proposals. So it's just a solid connected to Saturn, it's liquid, and they have thickness, etc. Then there was a kind of competition at that time, 1859. In that competition, they said, whoever explains what is this ring, they will win 130 pounds. And that time, if you just calculate it, 1859, and he was born 1831. So we just something 24 years old. And he did. I mean, in that period of time they gave, the only guy appeared to show that I solved the problem. It was Maxwell. Nobody else came. And he solved it exactly. And still, his solution is the solution. It took, I think, 1918. They went to Saturn, close to the ring, and they saw he was right after maybe more than 100 years. But what he did, actually, in this essay, this is a kind of proposal or thesis, let's say, but just to win this one, he just enjoyed it. And if you go through, it's 90 pages, like a book, and it is actually a book. You can find it even in libraries. And he just gave all the possibilities, and he, took them out, and he came to this point. The only way that this thing can be stable around the Saturn is if it consists of dust. Actually, dust, I mean particles. It's not liquid. It is not a solid connected to Saturn. It should be like what we see now. And now it is, observed and proved after so many years. So you can just imagine people were watching in the sky, but he calculated on the paper. And then it took 100 years, people go and see he was right. So how clever this guy was. He had other also talents. He also discovered actually nowadays everybody is amazed by looking at color TV or your mobile phone with HD, etc. But the concept goes back, the credit goes back to Maxwell, because he proved that only 3 fundamental colors here, red, blue, and yellow. So if you combine them, I was painting when I was a kid, actually not very much, so up to 15 years. I knew how to combine, the paint to get different colors. So I also use these three, main colors: blue, red, and yellow, to create other colors. But the point is, if you just mix them all, you get black. Okay, when they are paint. But for light, it is not like that. When you mix them all, it will be white. So he realized there are something in our vision, system, and also different from light. Although when you mix, let's say blue with yellow, again, even with light, you may get, green. But he realized it is not all similar to the paint. And then nowadays we know that in order to find different colors, you need only 3 layers of colors. And these are, valid for all devices that you use. So only they need 3 layers: blue, yellow, and red. So I didn't put anything about that, but you can go and read about. We come back to the Maxwell equation again, because Maxwell is known for his equations. There are actually, he gave the equations out of, I think, 16, but later on they were combined into 4. We have 4 equations. They are known as Maxwell equations. So we have here, let's say, vectors D, B, E, and H. So I gave the relation between D and E and D and H. Actually, E is electric field. Electric field is the one usually, I don't know, in high school they taught you electric field or not. Do you know what is electric field? You heard it. And D is almost the same, but D has also the effect of matter in it, understood? So that epsilon is the effect of matter. And the same for H. H is like magnetic field, but B has the effect of matter in it, understood? So they are almost the same, parallel for most of the linear matter. And okay, what the first equation says, they were very well known. The first equation says, when you have this row represents electric charge. When you have electric charge, you will have electric field. That's it. D represents electric field. So the one that I think you hear. But the second one says, see, there is no magnetic charge, there is no magnetic field. So magnetic produced by magnetic charge. Or in other words, there is no magnetic monopole. So we have electric monopole, but we don't have a magnetic monopole. The third one says, if magnetic field is time dependent, we will have electric field. I mean, that magnetic field will be surrounded by electric field. So if you have magnetic field produced by whatever, doesn't matter. But if it is constant in time, it's okay. But if it is time dependent, it will be surrounded by new magnetic electric field. And same for the other. Here, actually, this term was added by Maxwell himself. So this is the only term he added. So if we're going to say what is the contribution of Maxwell, I mean, quantitatively, but the fourth equation says current, electric current, J is representing the current. Electric current produces magnetic field. So magnetic field, we have it. So what produces magnetic field? And we understand no magnetic charge or magnetic monopole. So there should be other way. Other way is just moving electric charge. So electric charge, moving electric charge means current. Current is responsible for magnetic field. But also the additional term, we realized from the symmetry of the equations that he said something should be missing. Actually, it was also proved mathematically. So it said even there is no J, there is no current, we may have magnetic field by only time-dependent electric field. So if electric field is time-dependent, it will be surrounded by magnetic field. And then if magnetic field is time-dependent, it will be surrounded by electric field. And they are mixed together. So what happens here? Maxwell is famous for this equation because he was the first guy who unified the magnetic and electric, let's say, theory. Electric theory, let's see, I don't know how to call it because we used to call it electromagnetic theory, but it was electric theory and magnetic, they were going separate. But this was the talent of Maxwell, who realized everybody is wrong and they are related. And this is the unification of these two separated theories. Anyway, so this is the first unified theory. Now people are trying to unify all the forces, as you have counted 4 forces, but of course they were not successful yet. Coming back to okay, do you have any question after here? So you understand what is happening. Maxwell also said something else I didn't put here. He said, okay, if we have electric field and magnetic field in this room or anywhere in the space, they should satisfy this equation. So these are mathematical equations, so I can combine them. So he combined them, I didn't put here. And then he came across an equation, we know it now as a wave equation. And that wave equation, its solution is wave. So wave, actually you know wave. So then, and beating the equation, he realized the speed of that wave is something equal to the speed of light. But light was also known that time in optics, in the context of optics. So nobody thought about light would be, part of the electric theory or magnetic theory. Then he became a little bit in, sure. Light should be electromagnetic field or electromagnetic wave. So he knew that electric and magnetic field united here, they produce kind of wave. And then he predicted this wave is electromagnetic wave, he called it, it's same as light, or light is same as electromagnetic. So of course, these were all in theory. And I will talk about how it came into reality. So then you may think, okay, we say there is no magnetic monopole, and then electric charge is responsible for both electric and magnetic field. How about if there was magnetic monopole? What would happen? Just for those students who are curious in this regard, I give this equation also. These are if we have magnetic monopole. So this would be the form of Maxwell equation. And you can see that very much, symmetry. Actually, there are symmetries between electric and magnetic field. So these all are seen from this equation, not from what they knew at that time. Nowadays, physicists, they know very well, even students here, you might hear. Okay.
He discovered at the same time the principle of duality.
Yes, here, as I said,
Yes.
the symmetry.
Yes.
You see here, you can change E to B and B to minus E, and then you will reproduce the equation again. So I don't want to go through the detail of those stuffs. Let me just tell you what actually Einstein he said about Maxwell. He said after Newton, he is the greatest physicist. This is what Einstein told about Maxwell. And then he said, actually people they say, Einstein theory, Einstein stood up on the shoulder of Maxwell. So we know that is correct. Without Maxwell, there wouldn't be Einstein. So there wouldn't be anything actually now. We wouldn't be even here. No internet, nothing. Absolutely, we would be in dark. So now we owe him. His theory of electromagnetism nowadays is almost everywhere. So can we say he was the greatest physicist ever? Some people they believe it. Okay, Einstein is very clever. He was very clever. He did also big revolution. Newton also did. But what you see around? Do you see Einstein's effect except the GPS that you use? You may not see much. Okay, yeah, it's a thoughtful as a theory, but application-wise, we should, admire Maxwell. Maxwell changed the world, really, yes.
Little objection.
Yes, you can make it.
Because all the things that we formulated made by Faraday. Faraday was the technician, good experimental physicist. But he was not well educated like Maxwell because, as he said, Maxwell family was rich, got very good education, and he was very well known in the mathematics. But the first paper that we showed,
Yes, of course.
Showing the talent of Maxwell in such, hot.
Unifying the system.
Yes.
Yes, that's true.
So this paradigm made the experiment, evolved all the observations. One
Booklet. Yes.
booklet.
Yes.
Then one day he gave it to Maxwell. Maxwell formulated everything. Then he discovered symmetry, as Mr. just said. He discovered more than what Faraday observed. But Faraday triggered today's, I think, electromagnetic theory. And without the both of them,
Actually, it wasn't only Faraday. That's why I started from even, the others. Amperes. Yes, that's completely true. What I say, Maxwell theory, I think, not Maxwell himself, because of course, when we go back, Maxwell was stood on the shoulder of the others. So this is, in a chain wise goes back. But anyway, the idea, this is Feynman. This is what Feynman said about Maxwell. So you can read yourself. Maxwell's equation didn't just change the world. They opened up a new world in front of us. That is exactly. And also Feynman said the same thing. The most significant physicist in 19th century was Maxwell. But Maxwell, as you also said, he was from a rich family. He didn't need to work for, be worried about his life. I mean, kind of his life. So that's why his mind was free. Same as Newton. So the great, impact in science happened through these rich people. So unfortunately. Okay, coming to, we are approaching to almost end of 19th century. This guy, I think you know him. He's Röntgen. Röntgen has a double dot here, and I didn't put it because PowerPoint did not accept it anyway. So he was German, and this is he discovered X-ray. X-ray. They say he discovered accidentally or something, but there is nothing accident. They were, scientists. They knew. Okay, we don't know something. Now, suppose that one day you find there's a dark matter. It cannot be accident. So you were looking for. Of course, he didn't look for X-ray, and then he called it X-ray because he didn't know what it is. So we knew light, and by that time we knew electromagnetic wave, and he understood another ray beam is coming and has some effect. He didn't know from where it came from. Of course, we know now it's coming from atoms. So, and then it was, of course, produced at that time by certain atoms, or even now they use X-ray machine to produce it. I will show you a picture of X-ray machine. But it happened exactly 1895, almost at the border. And then this is the first. I don't know whether it is the first, but it's the hand of his wife. So he took the picture by X-ray. So you can just enjoy. And now this is an X-ray machine, how it is producing X-ray. As you can see, we have two, let's say, anode and cathode poles connected to a generator, the battery. And we have a tungsten here, and it gets heated up. And by heat, electrons getting up from the tungsten, and inside the, the potential difference between two poles, they accelerate, and then while they stop in the other, they reduce, because when they stop, they get accelerated, and then acceleration in electromagnetic means producing, electromagnetic wave, which X-ray is a small piece of electromagnetic wave. So X-ray, light, gamma ray, radio wave, the other things, even microwave, whatever we use, they're all part of electromagnetic spectrum. It's very, long spectrum. And they are, of course, characterized by certain things, which I will show you. This guy is a French physicist. So it's just, he was born after this. This is the only thing I can say at the moment. But he is very well known for nuclear physics. And at that time, there was no nuclear physics because they didn't know what is nuclear. Nowadays, everybody knows what is nucleus, what is atom, how atom is, consists of what. Anybody knows what an atom is consists of? Yes. So, we have a nucleus and electron orbiting as Bohr's model. Yes, and inside the nucleus we have proton and neutron. So both proton and neutron and electron, they were not known at that time. Understood? So put aside that. Anyway, this guy, what he did actually radioactivity. They realized uranium, which we know now is very dangerous. It emits some particle out. So then, together with Marie Curie, I think they got Nobel Prize after all. And coming to radiation, I said he discovered radiation. First uranium. Then these are the different types of radiation. The radiation may be in alpha particle. Alpha particle is actually in effectively the nucleus of helium. So if you take 2 electrons from helium atom, it becomes alpha particle. So some heavier substances they give, and radioactive substances they give alpha out. So 2 proton and 2 neutron together, bind together, they come out. It's called alpha. And it may be also beta. Beta is just an electron coming out from inside the nucleus. Nucleus is the small piece of atom. Actually, how we know that? We know from not Thomson. Thomson gave, anybody knows, because I think the Thomson model of atom also is given in high school. He gave a model before Bohr's model, and that is, of course, it failed, but he also is well known for the discovery of electron. And in this picture, what you see, this is the beam of electron passing, near a magnetic field and positive goes on a circle. And the gloomy path is due to the acceleration. So when they have acceleration, they emit. So this guy should be in our mind. He was born after all you have seen, and he lived unfortunately very short. You can see from 57 to 94. It's less than 40 years. So 37. So 37. Actually, he was active only 15 years in science. And if I show you, which I will, what he did, you will be amazed. If he lived 100, what we would be now, where we would be now. I gave this picture together with 3 more, scientists. This is Helmholtz. If you don't know who is Helmholtz, Helmholtz is known for physics student, or let's say our engineers, in one exercise in holiday, which we have Helmholtz coil. But generally, he is also one of the founder of electromagnet. But why he's pictured here? Because he was the supervisor of this. Understood? So he worked under his supervision. And then why these 2 pictures are here? You know them. One is Einstein, everybody knows. Who is this guy? Yes, Maxwell. What he did, he actually, after 8 years of Maxwell's theory, I can say exactly the time I didn't live. He produced electromagnetic wave in his lab. Understood? So electromagnetic wave, which was predicted by Maxwell in his Maxwell equation, he produced it. Nowadays we know as receiver and antennas. So we have antennas, they generate electromagnetic wave like radio station, the other thing. And there's also receiver, they get it. So he did both of them in his lab, and then he showed that what Maxwell said it was correct. So that's why he gave the theory of Maxwell, a kind of reality. But you know what? They asked him after he proved that Maxwell was right, his theory was really correct. They asked him, they asked him, what do you think this electromagnetic wave is good for? And what was the answer? You cannot imagine. He said nothing. it's just I did it because I wanted to show Maxwell, our master, he was right. He didn't even predict what would happen after a few hundred years. Now, suppose now if somebody asks us, what will be good if we discover gravitational wave? We really don't know. So we may say actually out of curiosity, but we don't know in future what will happen to the application of gravitational wave. So same at that time.
Einstein.
Yeah, they proved Einstein was right. So anyway, why Einstein's picture is here? Because Einstein also got inspired by this guy Hertz. Hertz works. I mean, he was an experimentalist. And what he did exactly, other than proving that Maxwell was right in producing a electromagnetic wave, you can see here. So at that time, 1879, electron wasn't known, but they knew there is current. So they said there is something going inside the wires. They knew. It was their idea of what is the mass of these currents. Okay, electric current. So they call it at that time inertia of electricity. So they didn't know what to call them even. And he made just experiment. He had no, theoretical background. Actually, he had, but he did everything. He found that then it's either zero or very small. And later on, electron was discovered, and we realized really it was very small. And also radio wave, he invented, actually produced. And electromagnetic spectrum, as we know now from X-ray to radio wave, he actually produced in his. He also in the very basic apparatus he made in his lab, he could also prove that the electromagnetic. Okay, we call it wave now, but that time they didn't know. Okay, wave. Electromagnetic wave, it's really wave. So how we know something is wave or not? So he knew that wave, light was wave, they knew, and the other mechanical wave. They get reflected, and they get also, we call it, other properties of waves. So in his lab, he made all the facility available to make sure that thing he produced is a wave. So diffraction is one of them. So diffraction means when light goes from air to water, then it is not normally. So it changed the direction. So then he could also prove that the wave he produced does the same. So and this photoelectric effect is related to us, and it is related to this guy also. Everybody, I mean, you all know Einstein for gravity. So, and you expected, I mean, everybody expect Einstein got Nobel Prize from gravitational theory that he gave, but unfortunately, or I don't know what to say, he didn't get from gravity. He got from the electric effect, which was, produced or invented, or let's say introduced to the community, physics community, by Hertz. So now what is it? Actually, this guy realized when ultraviolet wave is, directed to a metal, some electrons are coming out. The current is coming, and this is how you can see light with certain frequency, of course. When it hits a metal, he discovered electrons are coming out from. So he didn't know why, but he could produce. So this is called, as you see, photoelectric effect. And who explained it? Yes, Einstein explained it. When he explained 1905. 1905, the miraculous year for Einstein and for us, of course. He gave few papers, 4 papers actually. One of them was about photoelectric, and later on he got Nobel Prize for this. Coming to, again, closer to 20th century, I should check at time. So this guy, you see, he is very much looking at us from past. You see, you can see what he's thinking when he was looking at the camera. He put this picture for future. He put it for us. Look at him. And what is his name? He is Planck. Planck, actually, he was the guy who started the revolution, let's say, somehow, or one of them. There were some, anomalies at that time. They couldn't handle it. One of them is called black body radiation. I don't want to go through the detail because you are high school student, but this was one of them. There was an anomaly. I mean, they expected and the one they observed, they were not the same. So when you have any object with certain temperature, it emits electromagnetic wave out. Okay, so that electromagnetic wave, if you just plot it, the intensity, I mean, how strong with respect to frequency, it has, I mean, observationally, it has very beautiful graph. But what theory is behind? They tried all classical possible theory to explain it exactly, but they couldn't. So either at the beginning they have problem, or at the end. I mean, the inference of the frequency or the late frequency. So then this guy Planck started to solve this problem, and within the solution of, I mean, solving that anomaly, he came across Planck constant. So Planck constant, which is shown with H, is one of the fundamental constants in 20th century. So actually, he came across this equation. Anybody knows what is this equation? I mean, students, yes. Perfect. You see what he says? He said photon. Photon is actually light. So he is talking about photon light. Photon is, do I have time again?
Yes.
Should I go fast? Okay.
We'll have also discussions.
Okay.
Questions.
So that point is light at the same time is particle. So, and this is how Planck said for light consists of photons, particles, we call them photons, and this is the energy of particles, understood? So I go a little faster, and this is the spectrum, electromagnetic spectrum, and you see here, this is the small, gap, or let's say visible light that we can see, and you see how vast it is. And it goes from gamma ray coming from inside the nucleus to, a radio wave you can produce in the lab. So now, more you go to the, you can see the frequency, the thing here, like a spring, they show the frequency. More frequency, the more the frequencies, the more the energy they have, okay, carry, because H they represent the energy. F, I put by purpose this formula here because in high school they put F as frequency. So, but in scientific book they use nu. Coming to next important figure, you know him, Marie Curie. Actually, his full name is this one. After he married, his husband was Curie, so then Pierre Curie. Then she is known as Marie Curie. But Marie Curie was among the many physicists I mentioned, the only woman at that time. And Marie Curie was from, as I said, Poland, and she studied actually at the beginning in Poland. Then he moved to France. And then herself, she discovered polonium, and they call it polonium because of her. So he was a Polish. And then radium, and she got Nobel Prizes 2 times for that. Actually, the first was just for discovering the radioactivity. Second was for puring these elements. And then her students also, with her help, they also francium and the other. This is curium actually. Okay, so her own name. So now these 4 elements are because of Curie. This is for women in this room. So just see how significant a woman could be. So now some people they say she is the most influential woman, actually physicist of 20th century. You can see at least she's out of 10. Okay, we come closer. This is Millikan. Millikan helped to find, because we don't know yet electron. electrons mass per its charge. So we nowadays it's just granted everybody knows the electron, but that time they were killing themselves to understand what is the electron, what is mass, what is its charge, etc. So now this apparatus is called Millikan experiment apparatus, and this will drop oil experiment, and it shows actually we have it in our department, and we show our student engineering and others. So then we come to Rutherford. Rutherford, again we don't know yet atom. This experiment that you see is very much important because it was in 1911, and this guy also first he discovered atomic nucleus by this experiment, and then in 1970 he also discovered proton. So proton that everybody knows now. Now, what is this experiment? Alpha, some of the substances which they are radioactive, they give alpha out. They knew, and then they got a gold foil, and then just bombarded with these alpha particles. What they saw, because they didn't know what is the structure of atom, they saw that among the this is detected among the different angles, some of the alpha particles they come back completely. I mean, 180 degree back or close to 180. So then it would mean that those alpha particles hit something very strong, very, very heavy. And that is what they call it. Repeating the experiment, they call it that is the nucleus. So they realize the atom is just all void. You don't see anything, but certain points we have heavy, mass there, sitting there, and then they call it nucleus. So his influence after that was the atomic model Bohr gave. So now we come to Einstein. Einstein, everybody knows. Yesterday, since morning till before this talk, we were talking about Einstein. So I just shortly say what he did. He gave 4 papers in 1905, and one actually he gave more papers, but one more significant, most significant was in 1915. Actually, 10 years after the first. So a special theory of relativity. What is special in a special theory of relativity? Anybody knows from high school student? What was so revolutionary in his theory? I mean, a special theory of relativity, because it's very famous. He became famous actually from this theory. Actually, okay, that is the consequence. C is constant. I mean, the speed of light. Understood? So he postulated the speed of light is constant, but it was also supported by observation at that time. Then when you consider C is constant, I mean the speed of light, then you come to time is not anymore, absolute. Understood? So I have to say also Lorentz. I didn't put Lorentz picture here. Lorentz transformation at the same time or even before, they were also ready to be used, and Einstein used them. And Einstein also explained to the electric general theory of relativity later on, and also E equal mc squared. You just imagine these happened 1905, and within 40 years, in 1945, this theory, it was theory only, it killed more than 200,000 people in Hiroshima and Nagasaki. Understood? So it came to action less than 40 years. So this is the influence of the physicists. Anyway, we go on. This is Bohr. Bohr gave the Bohr, model of atom. He gave it very similar to our solar system. So nucleus at the center, and then electrons are orbiting. Thank you very much. So how you realize any proton? Thanks, Marwan. And thank you also. So as you can see here, proton and neutrons are inside the nucleus, and electrons are orbiting. The number of proton and number of electrons for neutral atoms are the same. Electrons are very light. Proton, neutron almost the same mass, 2,000 times bigger than electron. The force between them. Now, question. So let me just take the time. I will finish within 15 minutes. Is it okay? 10 minutes.
5.
5 minutes?
No, it's 5, 9 minutes.
Oh, 5. Okay, 9.
Then can
Okay.
continue with discussion section.
Okay.
Pass.
Okay, so then let me just go on
Summarize.
arguing. Yes. So now this is Bohr's model. We go further. You know, this is Schrödinger. Schrödinger, together with Dirac and together with others, they produced, or let's say they created quantum theory. It's the revolutionary theory, 20th century. Many students, they hate Schrödinger equation because they cannot solve it. But anyway, and this is famous Schrödinger's cat. Anybody knows what is it? You saw it before? So Schrödinger's cat explains, okay, at that time they knew radiation is a kind of a statistical phenomenon. The statistical means you know that after 1 hour, the radioactive element will emit, okay? Let's say certain, but this is not for sure when it will happen. So it's just a statistical phenomenon, probabilistically you can call. So then there was argument about the superposition, let's say, of the states. Then Schrödinger gave this thought experiment, kind of, you know, hypothetical. He said, suppose that we put this cat inside a box, okay? And we don't see the cat and inside at all. And there is a radioactive element here, and in 1 hour, 50-50, it will emit part. We don't know because it's statistical. So, but 50-50, it may or not, we don't know. And it was accepted because it's atomic scale. If it emits particle, then this guy, I mean the arm will fall, and then this vessel of poison will be released, and then cat will die. But if it doesn't happen, cat will be alive. So now question, after 1 hour, is cat alive or dead? So yes, that is exactly what Schrödinger meant. So when you're going to say what is the state of cat, you say 50% dead plus 50% alive. Yes. When you open the box, you exactly like quantum theory. When you measure, the system goes to a certain state. Then you will see whether it's alive or dead. Anyway, this is the probabilistic distribution of electron around hydrogen atom. Since we don't have time, Schrödinger found it actually. This is Chudwig. I think you know he discovered neutron. Neutron was very difficult to be discovered. You know why? I mean, electron, yeah, but proton and electron, they could be easier than neutron. Why neutron was so difficult to be discovered? Yes, has no charge, no effect you can have from magnetic, because the others, they have, you know, some interaction with magnet, but this hasn't got any. So anyway, in 1932, the neutron was discovered, and neutron, if he didn't discover neutron, the nuclear bomb wouldn't be made, because the bomb that they, you know, send it to Hiroshima and Nagasaki with a neutron, they were, you know, exciting the first initial atom, uranium, and then it was, you know, going to the further. So that's how 1932 and 1945, 13 years after. You can imagine how dangerous is science at the same time. And now these two pictures I put to just tell you, this is the stability line or stability region of all nuclei or substances in nature. And the blacks are completely stable. The others, they emit, and you can see the half-life. So usually we call when some substance is radioactive, what is the half-life? It means after how much time is the number of initial parents, we call it, atoms or nuclei will remain, so or they decay. So that is given here, and the blacks are stable, and the other. But when you look at here, we see our atoms or nuclei. They have Z, which is the number of protons, and number of neutrons. And as you can see, at the beginning, the number are the same, but when we get away, I mean, bigger Z and N, they get away from Z equal N. Actually, as you can see here, the number of N is bigger. So it might be because of electromagnetic force, electric force between photons, which they get more photons, then repulsive force causes it to become disabled. And what is this? Actually, this is also very important picture or figure. It shows you, we call it binding energy of stable nuclei. As you can see, the figure here is very interesting, because if you look at the speed of galaxies, the arms of galaxies in distance versus the distance from the central black hole, this is almost the same. The figure is the same, but what it says the binding energy when the number of the nucleus and both of them, proton plus neutron increases, but then it decreases. So fusion and fission comes from here, which I don't have time to go through. This is actually de Broglie. This guy, his name is Louis Victor Pierre Raymond, but we know as he was the Duke of de Broglie. So now we know de Broglie wavelength. So you said photon energy is equal h nu. Then he came across this idea. How about, because photon actually light is wave. So how about opposite we think? For particles we give a wavelength, and that is called de Broglie wavelength, and that is exactly equal to, this is what you already said, and this is lambda equal h over mc. H is again the Planck constant, and n is the mass of that certain particle, and c is the speed of light. So let me go on. This is Heisenberg. Heisenberg has a lot of let's say contribution in quantum, but this is very special. So I put it here. Anybody knows what is this? Yes, Heisenberg Einstein principle. So I know its name is written here. What it means? Exactly. So for subatomic particles, small particles, we cannot know their position. Position and velocity or momentum at the same time. So that is how it means. And this is Dirac. Dirac is great. His equation, Dirac equation, is still we are using. It's just a kind of advanced Schrödinger equation. So it contains the relativistic effect inside the Schrödinger equation. And finally, I came to the last point. This picture. This picture, actually, it is written where it was taken. So in 1927, I have to talk about all of them, most of them, but only I talk few of them. So this is to pay my all to them. So anyway, in another time maybe I go to the others as well. So if you have any questions, I am ready to